Today we will see Kirchhoff's voltage law or KVL in the electrical circuit. So this Kirchhoff's voltage law, also known as Kirchhoff's second law or Kirchhoff's loop law. So let's see this Kirchhoff's voltage law. So according to the Kirchhoff's voltage law, the algebraic sum of all the branch voltages around any closed loop in the network is zero at all instant of time. So let's understand this Kirchhoff's voltage law. So let us say we have one electrical circuit which contains one voltage source and three passive electrical components. Now here these components could be a resistor, a capacitor or a inductor. But in generalized way we can take them as a Z1, Z2 and Z3. And the voltages across these elements are V1, V2 and V3 respectively. So according to the Kirchhoff's voltage law, if we move around this electrical circuit and add the voltages that we come across each element in the circuit, then their algebraic sum is 0. So let us say we are moving in clockwise direction starting from this point A, and the first element that we come across is this voltage source Vs, and while we are moving from negative to the positive potential. So here we will follow the following sign convention, that whenever we are moving from negative to the positive terminal across any element, or there is a rise in the potential, then we will take that voltage as a positive voltage. Likewise, if we are moving from positive to the negative terminal across any element, then we can take that voltage as a negative voltage. So here, starting from point A, if we are moving in clockwise direction, the first element that we come across is this voltage source. Here we are moving from negative to the positive terminal. That means there is a rise in the potential. So we can take this voltage Vs as a positive voltage. Now from point B to the point C, when we are moving, there is a drop across this element Z1. So we can take this voltage V1 as a negative voltage. Likewise, moving across these elements Z2 and Z3, there is a drop across these elements. So we can take this voltage V2 and V3 as a negative voltage. And according to the Kirchhoff's voltage law, the algebraic sum of all these voltages is 0 in the any electrical loop. So you can say that Vs plus minus V1 plus minus V2 plus minus V3 is equal to 0, or we can write it as Vs minus V1 minus V2 minus V3 is equal to 0. That means Vs is equal to V1 plus V2 plus V3. Now, earlier we had seen that the voltage V can also be defined as E divided by Q, that is the energy required to move a unit charge. So we can write this equation in the form of energy as Es divided by Q is equal to E1 by Q plus E2 by Q plus E3 divided by Q. That means Es is equal to E1 plus E2 plus E3. So looking at this expression, we can say that the energy supplied by this voltage source is equal to the energy dissipated across these three passive components. So we can say that the energy supplied by the voltage source in the circuit is equal to energy consumed by the passive components in the electrical circuit. So we can say that KVL is nothing but law of conservation of electrical energy. So now let's take one numerical and see the application of Kirchhoff's voltage law. So we are given one circuit which contains two voltage sources and few resistors. So in this circuit we need to find the current I that is flowing in this circuit and the voltage across this 50 ohm resistor. So first of all, let's say the voltage drop across these three resistors are V1, V2 and V3 respectively. So let's apply Kirchhoff's voltage law around this loop. So as you can see here, apart from this 5-volt voltage source, across all other elements there is a drop in the potential. So we can write a KVL as 5 minus V1 minus V2 minus 2 minus V3 is equal to 0. That means 3 is equal to V1 plus V2 plus V3. Let's say this is the equation number 1. Now, according to the Ohm's law, we know that V can be written as I into R. So, we can write this V1 as I into 5, that is 5I. Likewise, we can write V2 as 10I and V3 as 15I. So we can substitute the value of this V1, V2 and V3 in this equation number 1. So we will get 3 is equal to 5I plus 10I plus 15I. That means 30I is equal to 3. That means I is equal to 3 divided by 30, that is 0.1 ampere. Now the voltage across this 50 ohm resistor is V3 and V3 is given as 15 into I, that is nothing but 1.5 volt. So in this way, applying Kirchhoff's voltage law, we can find the current and the voltage in any electrical circuit.